It's something like Francis. Bonahon is fine. Okay, so this thing doesn't work, but we can do this. Okay, so as you saw from the title, I'm going to talk about flags, snakes, and stingrays. But the real topic of the mini course is to give an exposition of this Fock-Goncharov classification of configurations of positive configurations of flags in Rn. So this is based essentially on this relatively famous paper. That paper is known to be difficult to read. So I'm using, my plan is to use you as guinea pigs because I'm trying to write a relatively elementary exposition of it. And in particular, so the flags and the snakes have been there. The stingrays came out exactly from these pictures, from these talks here. It's something I created for the purpose of these lectures. We'll see if it goes well or not. Okay, and so that's the expository part. And the main thing I would like you to get out of this mini course is why this notion of positivity is important. You know, when I was 10 or 11, I learned about negative numbers. I mean, prior to that, I only knew about positive numbers. And after that, I always thought that there was a symmetry in the world, positive and negative. Okay, for my bank account, I knew there was a difference. And for temperatures also, but somehow mathematically, I thought there was no difference. And there was it was like changing orientation in a manifold, you know, or something like that. And it's only recently that I discovered that there is a difference between positive numbers and negative numbers. And the difference is that positive numbers are stable under multiplications, whereas, as you know, negative numbers are not. And but if you're only concerned with the additive theory of numbers, there is indeed a symmetry. Okay, so that's what I would like you to get out of this mini course. The problem is that I don't know how much I'll be able to cover in these 5 lectures. So we're going to see. Yes, but I cannot use this. So, okay, so I'm going to start with the warm-up problem. So it's a problem in the plane, and you take P lines, and the plane, I consider it as a vector space, and the line is a one-dimensional vector subspace. Namely, they have to go through the origin. So you take P lines going through the origin, and you take another family of P lines, and you ask yourself, is there a linear isomorphism from the plane to itself, sending the ice line here to the ice line there? Okay, and so let's start. For P equal 2, it's pretty obvious that the answer is yes, because if you have 2 lines, you can pick a vector in L1, the first one, a vector in the second one, because they are distinct, that forms a basis for R2. You do the same thing for the L prime lines. So now you have 2 bases. You take the linear map sending the first basis to the second basis, and it is going to send the line L1 to L1 prime and L2 to L2 prime. Okay? So easy. 3 lines, you have to think a little more. Because, okay, so you start like this. You take a basis where V1 is in L1, V2 is in L2, and then the third line is spanned by a vector, which is a linear combination of V1 and V2. And so what you do is that you can change V1, you can replace V1 by lambda 1 V1, and so in this case, you can make lambda 1 and lambda 2 to be equal to 1. In other words, you found a basis where the third line is spanned by the sum of the 2 vectors. And you do the same thing with the prime lines, and then you take the linear map sending the first basis to the second basis. Where is that? And then obviously is going to send V1, so it's going to send V1 to V2, V1 prime, it's going to send V2 to V2 prime, and it's going to send the sum of the vectors V1, V2 to the sum of the vectors V1 prime, V2 prime, and so it's also going to send the third line without prime to the third line with primes. Okay, so that's simple. Okay, so let's start now with P equal 4. If I take two families of 4 lines, can always send the first line to the second one, and the first family to the second family, and the answer is no, because there is an obstruction. And this obstruction is the double ratio. So what's the double ratio of this family of 4 lines? So you take a vector in each of your lines, L1, and then when you have these vectors, this notation here represents the determinant of Vi. So when you have 2 vectors, there are 2 columns. So with 2 vectors, you create a 2x2 matrix, and you can take the determinant. That's what these terms are supposed to be. Okay, and so you take this double ratio because it's twice the ratio of 2 determinants, and it's specially designed so that it doesn't depend on which vectors you're taking, because so I was taking a vector Vi in the ith line, and I could take another one, like instead of V3, I could take 75 V3, but you see, if I replace V3 by 75 V3, then the top gets multiplied by 75, but the bottom also gets multiplied by 75, and so the ratio does not get, the ratio is the same. So this is uniquely determined. Right? Okay, and then if I have a linear map sending the first family of 4 lines to the second family of 4 lines, I claim that the double ratio associated to the prime family is the same as the double ratio associated to the original family. And it's something to do with the determinant. And it's because, to compute the double ratio associated to this family, I need to take vectors in the prime lines. Well, I can just take the images of the vectors in the no prime lines under this map phi. And so, this becomes, so the double ratio equal to this. Now you substitute phi of V1 instead of V1 prime and so on. So that's this. But then, by a property of determinants, the determinant of the images like that is just the original determinant of V1, V3 multiplied by the determinant of phi, because this matrix here is the matrix of phi times V1, V2. So determinants, and then you see 2 determinants at the top, 2 determinants at the bottom, they cancel out, and so you left with a ratio with no determinant, which was our original double ratio. Okay, so I have to go back here. Nope.
No, you have to press down.
Down? Down?
No. You have to press this screen first and then down. Yeah.
Okay. Okay, and so, so it is, so we have this theorem, which is the answer to the question for P equal 4, namely, you take 2 quadruples of distinct lines in the plane. There exists a linear map sending the first family to the second family, if and only if the double ratios are equal. So I just showed you only if, and then the if part, it's the same. You take the map. We saw that there was a map sending L1 to L1 prime, L2 to L2 prime, L3 to L3 prime, sending the first 3 lines to the other 3 lines. And then if you look at what you need for that map to send the 4th line to the 4th line, that's exactly the equality of these double ratios. Okay, so you do that by hand. It's very simple linear algebra. And I would like to say that it's so simple that it's very old. There is a very old name for this double ratio. So you have 4 lines here. That's L1, L2, L3, and 4. And then I'm going to take an affine line. So previously, these were lines as vector spaces, so they're all going through 0. Now I take a line that does not pass through 0, and I look at the intersection points. And then you do a little bit of linear algebra, and you find that the double ratio is also the ratio between these vectors. See, all these vectors here, they are in the same line, so you can evaluate the ratios. And when you evaluate the ratio, you find it's equal to that determinant. And here, there is a famous name for that. That's the cross ratio of these 4 points here. And so it's very old mathematics due at least to Pappus of Alexandria in the 4th century, or perhaps some famous Korean mathematician before. I don't know. You know, in the West, we always neglect Eastern mathematics and science in general. So you claim that, no, now it's working. Okay. Okay, and then that was the answer of the question for P equal 4. There is, you can build on that to get the answer for P equal P, and it's what you expect. Namely, except that I did something wrong. So the answer to the question for general P is that given...
Sorry about this.
Yeah, that's okay, yes. Okay, so what you can do is that you fix L1, L2, L3, and then you consider the remaining lines Li. So that gives you P minus 3 numbers with these double ratios. And you can show that the map is injective, and you can characterize the image. Namely, there exists a, given a family of numbers, you can find a p-tuple of lines whose double ratios are these numbers, if and only if it satisfies the following condition. Then all the di's have to be different from 0 and 1, and they have to be distinct. And okay, so it's a one-to-one correspondence. And in particular, we're going to that tells you that the number of distinct lines in R2, P distinct lines in R2 modulo the action of GL2, the general linear group. It has as many components as the space corresponding to these di's like this. So it's a factorial P minus 1 divided by 2. If I got it right, namely it's a number of orderings of these lines up to dihedral permutation, namely up to cyclic permutation and also reflection. So for instance, if you go back to the previous slide, you might have noticed that, yeah, except that I cannot go back. So how do I do this? I click here, I think, and I go back. No, I would, yeah. You might have noticed that I did not index L1, L2, L3, L4. So that they are in, so there are many ways to index them, and that's exactly what the signs detect. Okay, so these are lines in the plane. Now I'm going to switch to flags, and flags in Rn. So a flag in Rn, that's a family of nested spaces like this, where each space is strictly contained in the next one. And so in particular, that means that if the eighth space has dimension A. So you have a space of dimension 0, namely the trivial space, and then a space of dimension 1, a space of dimension 2, 3, and then n minus 1 and n. So in particular, the first one is always 0, the last one is always n. Okay, so when n equal 2, you don't have much space, you cannot have too many dimensions. A flag is the same thing as a line, because the first one, there are only 3 spaces. The first one has to be 0, the second one, the last one has to be the whole space, so the only one that counts is the middle one, namely the line. When n equals 3, you need a line and a plane, the space of dimension 1 and the space of dimension 2. That's why it's called a flag. So I went to look up the American English terminology. I don't know Daryl. So there is, in a flag, you have the space of dimension 0, that's the hand that holds the flag. You have the space of dimension 1. So in American English, that's a staff. In British English, it's what? Pole. It's the pole, yes. And then you have the piece of cloth going out. And so apparently in American English, that's called the fly, and in British English? Flag. Eh? The flag. I know, the flag is the union of all of those. Yeah. Okay, and I apologize. My very first slide, I put the flag for the American Math Society. I should have put the Korean flag. I should have edited my... Okay, so that's why it's called a flag. Eh? Okay, so in particular, there are 2 fundamental examples in Rn. The ascending flag, which is generated by the first, where the eighth space, the space of dimension A, is generated by the first A coordinate vectors, and the descending flag, where the space of dimension B is generated by the last B coordinate vectors. Eh? So it's a very important two flags. And on the rest of the slide here, you can scan it a little fast, but I would like to say that flags are important because they are intimately related to the structure of the group GLN. So if you learn a little bit about Lie group theory and Cartan subalgebra, using words like Cartan subalgebra, roots, blah, 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 so you start looking at something which corresponds to the diagonal matrices, and then you have one space which is a little more important, which is the Borel subgroup, which in practice corresponds to the upper triangular matrices in GLN. And then you have the opposite Borel subgroup, which corresponds to the lower triangular vertices. But in particular, so this is an important subgroup of GLN when you try to understand the algebraic structure of GLN. And flags correspond to the quotient of GLN by this Borel subgroup. And the way it works is that if you take E0, this ascending flag, you can consider its orbit under the action of GLN. So you consider the map which show to a linear isomorphism of Rn sends the image of the flag under that. And then that introduces, it's stabilized by the Borel subgroup, the ascending flag, and that introduces a bijection between the space of flags, between the set of flags and this quotient space. But then, you know, we're taking the quotient of a Lie group by a Lie subgroup. You know, you can put the structure of a manifold on that, and that's how you can put a structure of manifold over the space of flags, like that. But, okay, that's the blah, blah, blah here. That's not important. It's just a way to say that flags are not just weird objects like this. it's important to understand the space of the group GLN. Okay. So we had considered family of lines in R2, but I told you a line is the same thing as a flag. So a flag in Rn is the generalization of a line in the plane. And then we can ask the same question, which is, classify families of flags up to the action of GLN, up to isomorphism of Rn. That's, okay, so previously I didn't emphasize that, but it was really important that my lines were distinct. Because, you know, I was taking a vector in one and a vector in the other one, and I told you that forms a basis. Well, not quite. If the two lines are the same, the vectors will be collinear. That doesn't form a basis for the plane. So in the plane, to say that two lines are distinct, that means that they are in general position. Whatever that means, they are generic. And so let's do the same thing with flags. And another thing I would like you to get out of these lectures is that when you consider subspaces in Rn being in general composition, this is incredibly complicated. If you have only two of them, which is what's going to happen on this slide, it's fine. But as soon as you have three, it's very complicated. So, I'm just taking flag pairs, only two flags, then the situation is completely clear about what we're supposed to do. So, given two linear subspaces in Rn, well, they are, quote, in general position, whatever that means, precisely if they are transverse to each other, so that's the natural condition. And transverse means that, well, they're in generic position. So in particular, they take as much space as possible. So if you take the sum, its dimension, well, if it's as much as possible, it's essentially the dimension of the sum should be the sum of the dimensions. Well, except it cannot be more than n, right? You're in subspace of Rn. So it's going to be the minimum of these two numbers. Right? Okay, that's a good notion for transversality. Oh, but you know, why do you take the sum? You could also want the intersection to be small. And so if you take the dimension of the intersection, intuitively you look at codimensions, and you see that it should be the dimension of A1 plus the codimension minus the codimension of A2. Because when you take the intersection, you're cutting by linear relations corresponding to the codimension. So you expect the dimension to be this, well, except it cannot be negative, right? So you take the maximum with 0. Okay, so we take that, and actually these two conditions are equivalent, because if you remember your linear algebra class, you have this relation between the sum and the intersection. And so if one is as large as possible, the other one is as small as possible, fits nicely. So the two conditions here are equivalent. And the situation is completely clear for two vector spaces. And then when you have two flags, you just require that the linear space in one flag are in transverse to the linear subspaces in the other flag. And so what that means, that means this here, that's what I said. And so, and a typical example is the case where the ascending flag is 0, where the eighth flag is generated by the first A coordinates. You want it, it is transverse to the descending flag F0, where the B-dimensional space is generated by the last B coordinates. Okay, so that's an example of a pair of flags that are transverse to each other theorem, that's the only one. And so that in other words, up to the action of the group GLN, there is only one pair of transverse flags. And why is that? Well, by transversality, if you look at the intersection of the A-dimensional space of the first flag E and the n-a-1 space of the flag F, here, this intersection has dimension 1 by this formula. So it's a line. Okay, so in particular, for A equal 1, I get a line. For A equal 2, I get a second line. But you know, you can see, by linear algebra, L1 and L2, they actually generate the two-dimensional space of E. So in particular, the sum is direct. And then next one also, next one also, next one also. So you show that actually you have a direct sum decomposition of Rn. Okay, and then so to construct a linear map sending the ascending flag to E and the descending flag to F, you just take the linear map sending the 8th coordinate axis to this 8th line here, and I did everything so that it works. The conclusion that it's boring. So transverse pairs of flags, there is only one. Okay, so now let's go to triple. And then the quadruples, and then, as I said, transversality in Rn is quite difficult when you have more than two linear subspaces. Because when P is equal to 2, we had two equivalent definitions. One was that the sum of the two spaces is as large as possible. And the second one was that the intersection was as small as possible. And they were equivalent. But when you have three spaces or more, you have many more possible definitions. So the natural generalization would be to say that a family of P linear subspace satisfies the maximum prime property if it satisfies the first condition, namely if the dimension of the sum of the spaces is equal to either the sum of the dimension of the spaces or n, whichever is smaller. Okay, that's if you like to take sums, but you could like to take intersections. Okay, so then you would have the minimum intersection property if the intersection of if the dimension of the intersection is as small as possible, and so here you have to think about in terms of codimensions, and you find yourself that essentially you would like the dimension of this to be the sum of the dimension minus np minus 1. Okay, you do it in terms of codimensions. That's a clear condition. Except it cannot be negative, so you take the maximum of that with 0. And so that gives you this minimum intersection property. However, when P is LS3, they are not equivalent. And the simple example is the following. In R3, you take P vertical planes containing the x-axis. So you see that for these, the sum is as large as possible. It's the whole space. However, the intersection is not as small as possible because it contains the z-axis, whereas you would prefer the intersection to be 0. I mean, if it were in generic position, the intersection would be 0. Similarly, in R3, if you take P lines which are in the xy plane, well, their intersections is 0. It's as small as possible. But clearly, the sum is the xy plane, which is not as large as you would like, because you would like it to be R3, the whole space R3. So they are very far from condition. And as a side, so which one should we take? Well, we're going to see actually that they are sort of dual to each other. And so there is no reason to prefer one condition instead of the other one. But the main point is that they are not the good definition anyway. If you want to use the intuitive idea of saying that the P spaces are in general position, essentially it would have to involve something at the dimension of any space that you could describe from A1, AP using the symbol plus intersection and parentheses. So, you know, it's like this Kerek-Yarto problem in general topology, where you write all the subspaces you can obtain using complement and closure, I think, and intersection, perhaps. And so it's the same kind of, but here you have many more, and it's really unclear. Transversality of more than two spaces, that's really hard, which is another recent discovery in my life. Okay, so in particular, so we had a definition for definition of general position for linear surface. So I'm going to focus on the first one, the maximum span property. And I'm going to say that a flag triple satisfies this property is for every ABC, the subspaces contained in these flags E, F, and G satisfy the maximum property, namely if and only if the dimension of the sum of these spaces is the minimum of the dimensions, which in this case is A plus B plus C and N. Okay, now by stupid considerations, instead of looking at all the ABCs, you can restrict attention to those with A plus B plus C is equal to N. So this is this lemma. It's a stupid little lemma, which says what I just said. And the reason for that is that if you have this property for ABC N, and now you want to show it for any ABC. So for instance, if AB plus B plus C is strictly less than N, well, you can always find dimensions that are slightly larger whose sum is equal to N. And then you apply the property to these A prime, B prime, C prime. And you notice these inclusions, and then you think about it, and you see that it works. Don't try to read this. It's too complicated. It's very simple. You take a family of dimensions for which this dimension applies, and you use the obvious inclusions, and that works. So we can restrict attention to those where A plus B plus C is equal to N. Okay, and so we have the similar question. Given two so we saw that if I take two two transverse flag pairs, we saw that there is always a linear isomorphism sending one pair to the other. If you take triples, is it also true that there is a linear map sending these flag triple to that one? And the answer is no. There are obstructions, and they look like the double ratio of lines that we saw at the beginning. And they involve determinants. Okay, so Su-Young said, you have to be very elementary. So in particular, that's why I started talking about determinants. But now we need the grown-up version of determinants. So that's where this slide is coming from. Namely, we need exterior powers. Okay, I think here everybody knows about differential forms and therefore exterior powers. Let's do it anyway. So if you have a vector space, there is that thing called the exterior power, and it's generated by elements of the form V1 wedge, V2 wedge, Vk, where wedge is just a symbol. It's not, don't try to give a definition of that. It's a symbol where these Vi's are vectors in V, and then you want certain properties, namely you impose the relations that if you fix all coordinates except for one, Vi, the map with two Vi associate this wedge product is linear. So it's linear in each of the vectors. And then it's antisymmetric. Namely, if you switch two, you multiply by -1. Okay? Okay, and then this is a vector space. You can compute the dimension because you start with the basis for V, and then there is a well-known basis for lambda k, dimension of lambda k of V is n choose k. So in particular, it looks like a bad cut and paste here. So in particular, when k is equal to n, the dimension is n choose n, which is 1. Okay. And so any linear, and also what's really important that any linear map from a vector space V to a vector space W induces the map going from the exterior power of V to the exterior of W. And it's the stupid map where given a wedge product of Vi's, you take the wedge product of their images. That works fine if phi is linear. And a special case is the case where k is equal to the dimension of the vector space. So now that's supposed to be lambda n of phi, sorry. And it's a map from a one-dimensional space to a one-dimensional space. So it's multiplication by a number, and that number is exactly the determinant of phi. Okay, if you're a French person of my generation, that's actually how the determinant was defined to me. I mean, 2 by 2 determinant, I knew about a formula. 3 by 3 and above, that's how I was introduced to the definition. I'm on the generation where mathematics had to be as abstract as possible. And which is not my view of mathematics now. It has to be concrete. No categories in this talk. So, in particular, I start at 35, I start at 25, is it right? Or 30, 25, right? I have a math problem here. Okay, 25, that's just fine, yeah. So in particular, if a plus b plus c is equal to n, and if I have a flag triple like in the previous slide, if I have a maximal span flag triple, we saw that Rn is decomposed as the direct sum of these three flags. So that's the situation where we are. And so if I pick a vector in this eighth exterior power of the A-dimensional space of E, and then another element in the bth exterior power of the space of dimension B, and same thing here, I can take their wedge product, and that wedge product, I can interpret that as a wedge product in Rn, and this, whose dimension is A plus B plus C, which is exactly n. So it's an element of the nth exterior power of Rn. And I told you this piece of the space of dimension 1. And so it's a number, essentially, in practice. And in particular, because of the direct sum here, then this number here is different from 0. And that's really important. And the way you prove that is that you take a basis for Rn, which is well adapted to that, namely where the first eighth vector are in EA, the next B vectors are in FB, and the last C vectors are in G, in this space of dimension C, and everything is fine. So important is that these, so if I have these elements that are non-zero, their wedge product is non-zero. Okay, remember this for the next slide. So that will enable us to define triple ratio invariants, which are very much like the double ratio, except they are triple ratios. So the formula is complicated. If this is the first time you see it, it's incomprehensible. And if it's the second time, it may also be incomprehensible. So here is the formula. So given ABC and with A plus B plus C equal N, but also ABC be at least equal to 1, then we have this invariant where you take all these terms, which are exactly what I had on the previous slide. So I have 6 of them, and I take these triple ratio of them. So these are elements, these are essentially numbers, I told you on the previous slide. So you take the ratios of these 6 numbers like this, where these are elements of the appropriate exterior power of E, of F, and of G. Okay, now I told you that all of these numbers are finite and not zero, so you get that this is well defined. You never try to divide by 0. And this is not infinite. And also it's not 0 because at the top also it's not 0. So I emphasize that the reason for that is because on the previous slide, I used the maximal span property. Otherwise, I would have problems. And exactly like double ratios, you see that this triple ratio does not depend on the choices of these elements here, because what you notice is that each of them, let's take FB plus 1, for instance, appears 1 at the top here, only once, and 1 at the bottom. And you know, I'm taking non-zero elements here in R, in a one-dimensional space. So 2 choices are necessarily collinear. So again, I could replace my choice by 263 times my original choice. That would multiply the numerator by 263. That would divide it by 263, and therefore the ratio would be the same. That's the beauty of the formula. Okay, so it's definitely a number. And now, what's the next slide? Let's try to understand the formula a little bit. And so to understand the formula, you know, we have to understand this space of integers, A, B, C, where they are non-negative, and A plus B plus C is equal to N. And so that's the discrete triangle. That looks like something which appeared in Darrell's talk, because if you take, instead of taking integer, you take real numbers. That's a description of the two-dimensional simplex in R3. So it's a triangle, except that because you're taking integer coordinates, you have finitely many dots instead of having the full triangle. Okay, and so here are the dots. So ABC, so the vertices are the one of the form n0, 0, 0, 0, n, 0, n, 0. And then you have numbers, so each dot here is a pair ABC of integers whose sum is equal to n. And then if you look at the triple ratio, so first of all, I said they were indexed by numbers ABC, but this time ABC had to be at least 1, because look, you take A minus 1, so you don't want negative numbers. So in other words, these ABCs that index the triple ratio, they're actually in the interior of the triangle. Namely, they are not allowed to be on the sides. They are to be inside. Okay, so like this one here. And And then if you look at the term A minus 1, FB plus 1, AGC, if this is ABC, you can see that they are all on this little hexagon here. So that's a little easier to understand. It's a little harder to see where this one is. So it's one of these 2 points here, B plus 1. So it's this one here, I think. So I think this one, the point corresponding to this factor here is this one. The one corresponding to this one here is, I think, this one, and so on. So all these 6 terms are on the hexagon, and then you go top, bottom, top, bottom, top, bottom. Huh? That's exactly what the formula says. Right? So it's a better way of understanding a little bit what's going on. Okay, and then we have the same result as for double ratios. Namely, if there is a linear isomorphism sending the first triple of flags to the second triple, then necessarily all the triple ratios are the same. And it's essentially the same proof, but it's the grown-up version without determinants. Because, okay, so let's compute these 2 vectors. So to compute x of ABC, I take elements in the exterior powers corresponding to E, F, and G. And if there is a linear map sending E to F prime, of course, when I compute this guy, I'm going to take the images of my choices under the map. I told you that I have a map, phi induces a map between the exterior powers. Right? So it's natural to use those. Right? Okay, so I do this. That's my definition of the triple ratio E prime, F prime, G prime. And so I take the images under these maps here. So that's this horrible formula here. Yeah, but the exterior power, it was expressed in a stupid way in terms of wedges. So this operation is well designed with respect to the wedge product. So instead of taking the wedge product after taking the images under phi, I can do it before and I apply phi later. That's, namely, this is equal to that. And that's what that says. Okay, so I get a simpler expression now. And then these linter maps induced in degree n, they are linear. So the ratio, they are linear in dimension 1. So the ratio between the images under linear maps, that's the same as the ratio between the original numbers. And then same here. So this line here is equal to that line. And then that line, that was exactly the triple ratio to begin with. It's the same. There is the determinant here. It's the same proof as for double ratios. Okay, so if there exists a linear map sending one to the other, necessarily there will be they must have the same triple ratios. And then the theorem is a converse, and it says that 2 triple of flags here are, so the second triple of flag is the image of the first one under a linear isomorphism, if and only if the triple ratios are the same. And in addition, any set of numbers, of non-zero numbers, can be realized as triple ratios or some maximum span flag triple. So in other words, you have a one-to-one correspondence between the space of flag triples modulo the action of GLN and the space of potential triple ratios, namely R minus the origin to the power of the number of, this is the number of dots in the interior of the discrete arm. Okay, so that's what I would like to prove. And I have, minus 1 minute. So we're going to do that on tomorrow. Okay, so tomorrow I'm going to prove this, and then we'll see how it goes after that. Yeah.